Ya, bienvenidos todos. Gracias por participar de nuevo en un nuevo coloquio del Instituto de Física de la Pontificia Universidad Católica del Paraíso. Hoy tenemos a Eduardo Ibar. Él hizo su licenciatura y un magíster en astronomía en la Universidad de Chile. Y luego hizo su doctorado en astronomía en la Universidad de Edimburgo, en Escocia. Eh, y después hizo un postdoc en la Universidad Católica de Chile y ahora es profesor asociado de la Universidad del Paraíso y director ejecutivo de la Sociedad Chilena de Astronomía. Y hoy nos va a contar sobre su trabajo en el contenido de gas y polvo en galaxias a alto redshift. Así que, Eduardo, por favor.
Buenas tardes, muchas gracias por la invitación. Es un placer estar aquí virtualmente junto a ustedes. Voy a cambiar al inglés para se me hace más fácil hablar en inglés cuando es de ciencia. So today I'm going to talk about a recent study we have been developing in collaboration with some colleagues from Durham University, from Harvard, from Beijing, in which we have observed a sample of star-forming galaxies at high redshift, and we have used the ALMA observatory to look at the gas, the molecular gas, and the dust content in these galaxies. I'm going to give you a brief introduction for why it's important to do this kind of work. And there is substantial evidence that we live in a lambda cold dark matter universe, where we initially have something like 14,000 million years ago, a Big Bang, where the universe was extremely hot. And as the times evolves, so in this figure, as we move to the right, from the Big Bang to the right, the universe was expanding and cooling down. The matter started growing in larger structures, facilitating at some point the formation of the first stars, first galaxies, and then this matter evolved even the larger structures up to present day, where we can see massive galaxy clusters in the nearby universe. So within this, as the matter evolves, um, it's important to understand how what controls the evolution of galaxies as a function of redshift. And to do that, it's critical to understand the internal properties of the galaxies. So what's the dynamical state? How is the cycle of the gas? How the gas is transformed into stars, and how the stars then put the heavier elements into the interstellar medium, and then this cycle repeats over and over again. So to understand galaxy evolution, is necessary to look at different observables, such as the stellar mass content, the star formation rate, and well, metallicity, and obviously the physics of the ISM. Yeah, let's say in ionized gas, atomic, neutral, and also the dust. In the past, um, for more than a decade, the study of the high redshift universe has been divided in two main research groups. One of them, initiated by Charles Stadel, were finding dropout galaxies at high redshift, that is focusing in looking at the unobscured star formation. So using optical UV and UV light, they perform a description of the high redshift universe. On the other hand, in an almost entirely parallel world, is the study of the submillimeter galaxies, initiated by the development of submillimeter detectors at the end of the 90s. I would like to highlight the Scuba camera, which was mounted at the JCMT in Hawaii, and revealed for the first time a population of dusty star-forming galaxies, heavily obscured, forming a huge amount of stars per year in the high redshift universe. In this figure, I show you the star formation rate, so the number of solar masses being formed per year as a function of redshift using different tracers of the star formation rate. I'm going to concentrate here, for example, in the the tracers of the ultraviolet in deep fields such as good south HUDF, where it's easy to identify galaxies that lie below the 1 solar mass per year, even at the very high redshift universe. However, if we look at evidences, for example, using ALMA, a relatively deep observation, 870 micron, we detect mainly galaxies that are above the 10 solar masses per year, having so this gap between the sensitivity of 2 millimeter detectors and the UV has been has separated both research groups in the past. So there has been a big, strong consensus that if we look at the star formation rate, the cosmic star formation rate density, so the number of solar masses per year being formed per unit of comoving volume, we uh, it has been seen that using ultraviolet uh, tracers, there is a steep uh, increase from redshift 0 up to redshift roughly 2, and then another decline at higher redshift. This has also been observed using infrared evidence, mainly thanks to the appearance of the Herschel Space Observatory, in which uh, both tracers of the star formation rate tell us the same story, that this is an increase of the star formation rate density up to redshift 2 and then a decline, although UV can only prove that at redshift higher than 3. Infrared is quite difficult to obtain detections at this redshift yet. So what's causing this shape of the cosmic star formation rate density? There is a strong evolution of the luminosity function of far infrared emitters. Here I show you well, the luminosity function as a function of infrared luminosity, where in gray you see the luminosity function of low redshift universe, and in orange at redshift higher than 3. That means that a normal galaxy in the nearby universe, again, a very bright and luminous galaxy in the nearby universe is relatively normal in the high redshift. So this strong evolution causes also the the significant increment in the number of stars being formed in the high redshift at higher redshift. I'll put here another two drivers that can have a role in controlling the shape of the cosmic star formation rate density, which is the cosmic molecular gas density. In this sense, is the CO, the molecular gas traced by the CO molecule per comoving volume as a function of redshift. It has been found that it seems like there is a steep increment following a similar shape as the cosmic star formation rate density, but in the amount of molecular gas. This could be understood as if you have more gas, if obviously you can form more stars, and that might explain why we have this shape. On the other hand, I would like to put this other example. We have seen that the number of mergers or interacting galaxies as a function of redshift seems to increase, and the number of merging galaxies at nearby universe are much lower than what you can see at higher redshift. This is important considering that the interaction of galaxies can perturb the dynamics of the galaxies, and the gas can lose angular momentum and fall into the central regions, generating, for example, nuclear starburst, enhancing, obviously, the star formation rate. And that might be another reason why at the peak of the cosmic star formation rate density, why we see a peak in the cosmic star formation rate density. Maybe merging activity has a role. So in this work and this presentation, I would like to focus on a sample of star-forming galaxies observed at high resolution at different multi-wavelength tracers to characterize the internal properties of these galaxies. What is this? The survey that I'm going to focus is this called Heisel's survey, the High Redshift Emitting Line survey. This survey imaged a significantly large area of the sky, something like 5 square degrees, in fields like SA22, Cosmos, and UDS that have plenty of multi-wavelength coverage, so facilitating the description of each detection. The survey was taken in broadband imaging and narrowband imaging, especially in the near infrared, in Z prime, J, H, and K. And the narrowband filters that are within the range of the broadband filters. So the idea is that if we perform this analysis and we hope that a line emitting galaxy is redshifted, so the line emission falls into this filter, this narrowband filter, this or this, we can identify in a relatively easy way significant numbers of line emitting galaxies at high redshift. This is one example. For example, this is a galaxy at redshift 1.5 in which we have an H band image. The narrow band in the H band, if we subtract these two and scale them properly, we can identify excess in the narrowband filter that can be associated for a line emission. This is the Z prime and the narrowband filter in the Z prime. The same thing, you can identify a galaxy that have a line emitting falling into in the narrowband filter. In this sense, we can obtain a sample of galaxies at different redshift. For example, if we concentrate only in the H alpha emission, we can select galaxies at redshift 0.4, 0.8, 1.5, or 2.2. This survey has been used in the past to calculate, for example, the luminosity function in H alpha, and finding again that there is a strong evolution of the luminosity function in agreement with a strong evolution of the cosmic star formation rate density. In this work, I'm going to concentrate in the sample of galaxies that lie at redshift 1.5 and 2.2 that have luminosities lower or similar than the break of the luminosity function. And why I'm going to concentrate here? Because I'm going to talk about typical or normal galaxies at high redshift, in the sense that they are the most numerous ones and not the rare ones that lie above the knee of the luminosity function. The sample has star formation rates that are higher than 3 solar masses per year. So I'm going to focus in those galaxies. The first campaigns we performed were to, considering the large number of line emitting galaxies identified over 5 square degrees, we were able to identify several of them to be located close to a nearby bright star within 30 arcsecond at this magnitude. So in that sense, in that subsample of the Heisel's galaxy, we were able to trigger adaptive optics observations using integral field unit with Symphony, obtaining kiloparsec scale resolution of something between 0.1 and 0.2 arcsecond resolution for these galaxies. The sample compiled recently by Gilman, shows that if we look at the star formation rate as a function of stellar mass, and these lines show the so-called main sequence, the sample we have observed is mainly composed by main sequence galaxies. Some of them are a little bit higher in star formation rate, but roughly are in the range of being normal or lying below the knee of the luminosity function. The symphony of observations of the high cells, we call it shy cells, revealed that the galaxies have high surface brightnesses, have wide kinematical parameters, and a significant number of galaxies that were dominated by dispersion, so, and gravitational fragmentation on kiloparsec scales. So, in other words, gravitational fragmentation, I mean that there are clumps in the H alpha maps. The observations reveal the presence of turbulent disks, thick disks that are highly pressurized with gas collapsing in massive star-forming clumpy complexes that could be even up to 1,000 times more massive than the star-forming regions seen in the Milky Way. So these are extreme star formation activity over at high redshift, even though these look normal in the luminosity function. We complemented, thanks to the work developed by Juan Molina from Universidad de Chile, who worked together um, to increase the number of galaxies for this Scheisels campaign. We obtained intensity maps, velocity maps, dispersion maps, and this is a residual after removing the model to the velocity field. We have dispersion dispersion profiles and rotation curves that can be used to estimate dynamical masses and, all the dynamical parameters. So today we have a sample of 34 galaxies that have been observed with adaptive optics, with integral field unit spectroscopy in H alpha, and a small sample in O3, all of them at kiloparsec scales, and you can find more information in these three papers. Something we identified from the H alpha kinematics is that if we look at the, the asymmetries of the emission of the H alpha emission with respect to a soft or thin disk, all perturbations with respect to a disk, let's say parameterized by the kinetimetry, we identify that galaxy mergers or galaxies that show more perturbations seem to increase as a function of redshift, as similar to what I was talking before, where it's maybe the, the star formation rate at the higher redshift universe might be triggered by an enhanced for more interaction between galaxies. Using also the N2, well, the H alpha, the nitrogen 2 doublet at each size of the H alpha emission can be used, the N2 to the H alpha, as a rough estimate of the metallicity. And this can be seen in different annuli from the dynamical center as a function of radius. We have seen that this ratio decreases as we move to the outskirts of the galaxy in most of the cases which were detected. And in this particular case, this galaxy was classified as a merger. So it's not well distributed, gas is not well distributed and might be more complex and difficult to give an interpretation of the metallicity dependency in a disk-like galaxy. What about the obscure star formation rate? We have seen only the H alpha corrected by extinction some level, but what about the obscure star formation rate? We, in the past, developed, after the appearance of the Herschel Space Observatory, I performed an analysis of the high cells galaxies, specifically focusing at those at redshift 1.5. I stacked all the population using WISE imaging, Herschel imaging, and Scuba and Aztec mapping in the cosmos and UDS fields. I was able to characterize the typical spectral energy distribution at far infrared wavelengths for the galaxies at redshift 1.5. Considering the large number of galaxies from the Heisel sample, I was also able to divide the sample in terms of stellar masses. A sample of very high stellar masses and something lower and something in the middle. If I assume that the integrated far infrared emission is related to the amount of extinction suffered by the H alpha emission, we can, I was able to put these Heisel's points to derive the amount of extinction as a function of stellar mass being suffered by these galaxies. As expected, the most massive galaxies tend to be more luminous, more affected by extinction than the low massive ones. On this uh, shaded area shows the parametrization by Garn and Best using SDSS galaxies, nearby SDSS galaxies, and surprisingly, there's a really good agreement between this parametrization with respect to what is seen in this sample at the at redshift 1.5. Having in hand the typical far infrared emission for Heisel's galaxy, we were ready to estimate how much time it will take to the ALMA to the ALMA observatory to look at the emission, at the Rayleigh-Jeans emission of these typical Heisel's galaxies. So far, we have observed 9 galaxies at zero point 0.2 arc-second resolution in dust, so matched to the symphony imaging. So always looking at the possibility to describe the star formation from the obscure perspective and compare it to the unobscured H alpha imaging. The data these observations usually take an hour of observing time, and for resolving the galaxy at this resolution, the data has been reduced, typical following standard script for PI up to calibrated UV products and performing T-clean imaging with different weightings and tapering. This is one example. We observe in ALMA a compact core at an extended emission. When we compare it to the symphony imaging, this is the H alpha intensity map of the moment zero mapping. It has the same direction of the, let's say, the dust. So that's good. But the H alpha doesn't show any interesting emission at these very bright spots revealed by ALMA. And actually, if we compare also to HST images, this is an image of the rest frame UV emission, we find that the morphologies are totally different for this particular case. This is being submitted by Rachel Cochrane from Harvard and presents that there is a clear, it's a very complex, even looking at normal galaxies, we are talking a very complex ISM state in these galaxies. The dust one hand reveals something totally different from H alpha, and H alpha totally different from HST. So, and this is, remember, at observations at kiloparsec scales. So when we look at kiloparsec scales in the Milky Way, we can easily average the properties and everything looks, the scaling relations looks fine. But here it seems like the ISM is totally different in if we look at different things. The sample, as I mentioned, was 9 galaxies observed. And here we have a HST image at the right, at the left-hand side that traces mainly the stellar emission. Here we have the UV emission. This is moment 0, H alpha emission from Symphony. This is the high resolution ALMA image. And this is the tapered ALMA image, just to show you the kind of to integrate total fluxes for these galaxies. Another beauty image. Here we have an example of one galaxy that in the H alpha shows this kind of T morphology. In ALMA, we look like a triangle offset from the H alpha mission. And in the background, in colors in red and blue, we have the stellar component and the UV radiation. It's not at kiloparsec scale. You can see there's not located the same region, the same, and this for other case is a bit more well behaved, where the ALMA continuum is on top of the H alpha mission and also in the peak here observed by HST. Something to take a note. I forgot to mention this is a work mainly developed by Cheng Cheng, who was a former postdoc at the University of Valparaiso, and now he's in Beijing. The detections we have found, so if you look at the left-hand side figure, we have the N2 to H alpha, which is a proxy for metallicity in the y-axis, and the x-axis we have the stellar mass. Out of the 9 galaxies, we only detected in continuum the ones that have stellar masses higher than 10 to 10 to 10.5 solar masses, and those ones with the higher metallicity or higher N2 to H alpha ratio. This is important for developing future ALMA campaigns to have more success and the number of detections. On the right hand side, I put the integrated far infrared, the integrated star formation rate traced by the far infrared emission in the y-axis, and the star formation rate traced by the H alpha emission. In red are the observed galaxies in this campaign, which are relatively, well, are in agreement within the scatter, let's say. The uncertainties are mainly dominated by the assumptions behind the integration of the star formation rate in the far infrared and the correction for extinctions for the H alpha. So, but roughly we can say that this kind of agree within the scatter. Something really important to we found is that effective radius as a function of far infrared luminosity in light gray, I don't know if you can see it properly, but the ones that are in this region are galaxies that are in the nearby universe from the kingfish and gulls samples. On average, the size, the effective radius of these local star-forming galaxies are between 3 to 4 kiloparsec on average. But if we move to the high redshift, let's say taking samples from the Dancing ALMA or samples from Goldberg 2019, mostly submillimeter galaxies, it is found that these galaxies are much more compact and with scales, typical scales from 1 to 2 kiloparsec. Our sample in red here shows that we are looking at a sample of galaxies that lie at similar redshift than these ones, but we are at the upper end of the size distribution for these galaxies. So, and also, we are not looking at the very bright galaxies, but we push these limits to lower luminosities as we are looking, as we are selecting galaxies that comes from H alpha observations. Here, so we identify galaxies that are very big in size, probably talking about uh, a more normal star forming activity happening in extended disks rather than compact cores. We were even able to identify, for example, for this particular case I showed you before, this we have a, a bright uh, core in ALMA and nothing seen at the same position in HST or Symphony. If we look at this function, for example, the star formation rate and surface brightness, so solar masses per year per kiloparsec square, in different annuli, from the center of the galaxy out to the outskirts, we see here you can see the ultraviolet prediction without correction by extinction. In green, the H alpha prediction without extinction correction, and in red, the dust estimate um, for the star formation rate. If these two are corrected by extinction, by standard corrections, we move this up to a similar value as the one predicted by ALMA in dust, but at distances beyond 4 kiloparsec. If we move to the center of the galaxy, ALMA is the only one that is able to reveal a compact core with almost 100 solar masses per year within a small region, within a kiloparsec scale. So basically, this compact core here only revealed by ALMA and not the other proxies. Considering that we have a dust emission and H alpha, we can also construct extinction maps. Here, this is this one particular galaxy where this is clearly extended. If we compare the H alpha with the far infrared, we find that the extinction of the H alpha emission at the center should reach values of six magnitude much higher than the typical correction of 1 magnitude performed in the H alpha at this for samples like this. Even in the disk, we are observing something between 3 and 4 magnitudes in H alpha extinction. Something to highlight is that this particular galaxy shows a compact core, but also extended emission. So it has very similar properties which are similar to submillimeter galaxies. Indeed, this is one of the brightest galaxies in the sample, and has been previously detected also by Herschel and other um, Spitzer and in other bands in the infrared. But also would like to highlight these two other points, which are JVLA observations that reveal that the source is not, it doesn't have a compact, let's say, a flat spectrum at radio wavelengths, but a negative radio spectral index, typical of 0.7, 0.8, which is similar to the ones found for typical star-forming galaxies. On the other hand, when we compare the amount of radio emission to the far-infrared emission, so looking at the far-infrared radio correlation, we don't identify that there is a radio excess for the signal, so not suggesting the presence of an AGN in this particular galaxy. We obtain JVLA observations at 6 gigahertz at much resolution, roughly one arc second resolution, revealing the same bright center as revealed previously by ALMA. So we're pretty confident that this is a very young proto cluster of it's a young proto bulge of being generated at redshift 2.2 in this galaxy. What about the molecular gas content? The molecular gas content in Heisel's galaxies, we started a while ago with different campaigns with ALMA in early cycles and Plateau de Beurre, targeting the CO221 and CO322 for galaxies at redshift 1.5 and 2.2. So we selected 2.1 for galaxies at 1.5 and 322, CO322 for higher redshift galaxies. These images show, for example, moment zero intensity images for the CO emission from Heisel's galaxies. Some of them, uh, in order to enlarge the number of galaxies with observed CO um, CO with observed CO with CO coverage, we increase the sample, not only including those that have been observed with the symphony, but using galaxies that have been observed with KMOS. I included the KGS galaxies, targeting something like 20 galaxies in CO221 and CO524, uh, which we have found something similar in that the rate of detections here we have in field circles, the ones that are detected, and not field circles, the undetected ones. We have found that most of the detected ones are those with higher stellar masses, although the difference between uh, the in 2 to H alpha ratio is not entirely clear, the separation. We have over 20 galaxies observed with our projects, plus other 40 galaxies have been identified from the ALMA archive, having CO coverage for galaxies that have been previously observed with the KMOS, with OSIRIS, with NIFS, other integral field unit, um, such as just a symphony. So we are in enlarging the sample of the galaxies observed in CO, thanks to the help by Alejandra Munoz Arancibia, who created a very interesting code that can interact with the ALMA archive in a very simple way and can extract the cubes, which are of scientific interest for. We are going to publish this soon, but preliminary results: the molecular gas masses are of the order of 1 to 5 solar and 10 to 10 to the 10 solar masses. The gas fractions imply values of something like 20 or 80% of the mass is in molecular gas. So plenty of reservoir of gas to form stars. And interesting also is that the depletion times, so the time it takes the molecular gas to be consumed at a given star formation rate, is of the order of 1 to 10 giga year. So we are talking about a long-standing mode of star formation for normal galaxies, for these Scheisels galaxies. This campaign has been mainly performed at low resolution. I would like to highlight that because we first need to identify what's the total amount of CO emission and then trigger a higher resolution imaging. Indeed, a couple of sources have been observed at high resolution. This is one case. We observed CO221 at 0.15 arc-second resolution, revealing the internal dynamics of the molecular gas, where we find velocity dispersions of the order of 100 kilometers per second. And when we compare this value to the rotation velocity, we find a ratio between these two of the order of 1. So very turbulent disk, rotating disk. This figure on top shows the CO221 velocity field, the velocity minus the model, and the dispersion. And this is the rotation curve. And the bottom, we have this the same galaxy, but observed with H alpha with symphony. We find that the position angle and rotation is on the same direction, which is good. And the the dynamical parameters which are very similar between what is revealed in H alpha and CO. This has been published by Juan Molina in 2019. Considering that the H alpha is a proxy for the star formation rate and the molecular gas is a proxy for the molecular gas content, we can explore the Schmidt-Kennywood law at redshift 1.5 for these galaxies. In particular, Scheisels 19 is the one shown here. If we divide the galaxy in different annuli to calculate the molecular gas surface brightness and the star formation rate surface brightness, we find that this galaxy lies at the same star formation efficiency as seen in normal galaxies in the nearby universe. In other words, if we consider normal galaxies of the high redshift, the Schmidt-Kennywood law is still valid for these these high redshift galaxies. The dynamical parameters and the fits to the IFU data or the ALMA data allowed us to calculate the dynamical masses, which also put constraints. For example, the fraction of dark matter fraction can, we have the dynamical mass, the stellar mass from the SED fitting, and we can put constraints on the alpha CO conversion factor, finding for this case values of the order of 2 solar masses per year, sorry, 2 solar masses per these units, and a dark matter fraction of the order of 50% for this particular galaxy. To finalize, I would like to say that this is a really is a new ALMA project that has a new in the sense that is going to appear on AstroPH very soon, which targets the dust and the molecular gas content in galaxies at redshift 1.5 and 2.2. The dust is I will leave the summary there for you if you that's all. Thank you.
Muchas gracias, Eduardo. Súper interesante. ¿Preguntas?
Sí, ¿puedo preguntar?
Sí, sí.
Sí, interesante. Gracias, Eduardo, por la charla. Pregunta sobre, me llamó la atención la razón tan, digamos, la razón de la velocidad de rotación sobre la dispersión de esta galaxia, que es cercana a 1. ¿Cómo se compara eso con las de más bajo redshift para las que siguen la misma ley de, digamos, la Schmidt-Kennywood es la misma o...?
No, esa fracción es considerablemente más baja a bajo redshift. En otras palabras, la turbulencia que existe en el disco es significativamente menor en galaxias de bajo redshift comparado con las que están en alto redshift.
Pero aún así la misma ley Schmidt-Kennywood se estaría cumpliendo para ambas.
Sí. Hay una separación acá en brillo superficial. Obviamente acá están las que son de más baja, pero incluso en ambientes que son de alta densidad, también digamos, continúa esta relación. El origen de la dispersión no es, no está definido cuál sería, qué es lo que está produciendo la mayor dispersión eh, en los discos a alto redshift. Hay harta discusión sobre eso y es una de las tareas que queremos atacar con imágenes de mayor resolución.
Pero se podría inferir de forma indirecta que entonces esta ley no tiene que ver con turbulencia. O sea, la turbulencia no estaría jugando un papel importante. ¿O no? ¿O no es tan directa la lógica?
No me arriesgaría a decir eso, pero no tengo una respuesta concreta. No sé.
Me parece bien, gracias.
Gracias, Nicolás, gracias, Eduardo. ¿Alguna otra pregunta? Una pregunta, ¿tiene alguna idea de el tipo de galaxia al que va a evolucionar esa muestra que están observando ustedes en el presente, digamos, a redshift 0?
A ver, eso. A ver, supongamos. Ahí se me fue. A Redshift 2 son cerca de 10 billion years, ¿cierto? 10 billones de años, 10 gigayears. Estas galaxias consumen su gas del orden de 1 gigayear a 10 gigayear. Por lo tanto, digamos, podrían transformarse en galaxias que estén ya sin formación estelar, rojas. Habría que calcular cuál es el redshift de lo que esto ya se transformaría, asumiendo que no hay acreción de gas que las mantenga formando estrellas. Si es que está aislada, claramente terminaría una galaxia roja, digamos, no sé si elíptica o no, pero sin formación estelar, que antes de estar en redshift 0. No sé si respondo a tu pregunta, pero todo depende si es que hay acreción de gas o no.
Gracias. ¿Alguna otra pregunta para Eduardo?
Sí, a mí me gustaría preguntar cuál es el entorno típico donde se encuentran esas galaxias.
Estudios de entorno no los hemos desarrollado. En general, estas galaxias están seleccionadas en el campo sin querer buscarlas en regiones de alta densidad. Existe la posibilidad de hacerlo en campo SA22, donde existe una mayor sobredensidad de galaxias, pero esta galaxia en particular no la hemos analizado de esa manera, así que te diría que son galaxias de campo, que no están embedidas en grandes regiones o sobredensidades de galaxias.
Ok.
¿Alguna
Oye, y otra
otra?
pregunta, si no nadie pregunta, hago otra. Con respecto al código este que habíais estado desarrollando para poder obtener datos de archivo de ALMA, ¿ese código estará disponible o está disponible?
No sé si Alejandra está en el público que pueda opinar.
Estará próximamente en GitHub como plataforma.
Genial, gracias.
Es bien práctico. Python.
Alejandra es la experta en este tipo de funciones computacionales que son... Eso es súper útil porque es capaz de identificar, por ejemplo, como input, posición, right ascension, declination, y le coloco, no sé, un redshift, y te identifica de todas las observaciones que ha tenido ALMA, cuáles, de qué proyecto cubre esa región de frecuencia en esa posición. Así que, como dice Alejandra, debiese estar en GitHub
Pero
para que
para
sea
hacer
público.
cosas también el mérito es del módulo AstroQuery de Python. Entonces este código hace uso de ese módulo estratégicamente.
Ya, buenísimo, porque AstroQuery es una herramienta súper potente y si además estás usando eso, imagino que debe ser súper útil y va a ser bastante agradecido por la comunidad.
El único problema, lo advierto, es que hay que bajar los datos. Entonces, cuando tú quieres bajar los cubos o los datos raw, ya digamos, la transferencia de datos te mata y te va a tener que estar bajando un montón de información que al final, sí que, digamos, para una muestra grande se complica bastante. Idealmente, podría ser una herramienta que esté online, que te permita sacar ese rango que te interesa de los datos y no tener que bajar todos los datos para hacer el análisis. Eso es algo que se podría desarrollar en plataformas online, en la cloud o algo así.
Sí, se me ocurre alguna idea, pero bueno, se puede conversar más adelante.
Súper.
Bueno, si hay alguna última pregunta. Si no, agradecemos de nuevo a Eduardo por su disposición, por la charla, y como dije al comienzo, la charla está disponible y va a seguir estando disponible en el canal de YouTube del instituto. Así que gracias, Eduardo, muchas gracias a todos por participar y hasta la próxima.
Gracias por la invitación. Chao, chao.
Gracias.
Chao, gracias.
Chao.